Welcome back, everyone. Ready for another deep dive? Today, we're taking a look at something you use all the time, but probably don't think too much about.
Large language models.
Exactly. The brains behind those chatbots everyone's talking about. But we're going deeper than just, what they can do. We're going to be exploring the hidden geometry of how these LLMs understand language.
Yeah, it's kind of like mapping constellations, but instead of stars, we're looking at how words and concepts are arranged in the LLM's own little world.
We're going to be breaking down some really cool research that's trying to do just that. And, get this, it suggests that the way LLMs organize all this information might be directly tied to how well they actually perform.
Really makes you think, huh?
It really does. So
Yeah.
where do we even begin with something like this? I mean, how do you visualize this geometry? It all sounds a bit abstract.
You're right. It's not like we can just crack open an LLM and see like words arranged in neat little rows.
Right.
But researchers have come up with some pretty clever ways to study how these models represent language. And it all starts with something called tokenization.
Tokenization, yeah, that rings a bell. Isn't that how LLMs break down language into smaller parts?
Exactly. It's like when you read a sentence, you naturally break it down into individual words to understand what it means. LLMs do something similar, but sometimes instead of whole words, they break things down into these fundamental units called tokens.
Okay, so like sometimes it's a whole word, but sometimes it's just part of a word.
Yeah, it all depends on what makes sense for the LLM to understand the meaning.
Makes sense.
These tokens, they're like the basic building blocks of meaning for the LLM. But here's where it gets really wild. Each token is then turned into a set of numbers, like coordinates in a high-dimensional space.
Wait, hold on. So each word or each token becomes a point in space with coordinates.
Exactly. Like imagine a vast multi-dimensional universe. And each word, at least the way the LLM sees it, exists as a point in this space.
Yeah.
And the relationships between all these points, like how far apart they are and how they're clustered, that's the geometry we're talking about.
Okay, now my brain's starting to hurt a little bit.
It's a lot to wrap your head around.
I'm trying to keep up. So if each word is a point in space, how do researchers actually measure the distances and relationships between them? Are there like special LLM telescopes?
No telescopes. But there is some pretty complex math involved. One of the things they look at is cosine similarity. Imagine two arrows pointing in different directions. Cosine similarity measures how much those two arrows are lined up. If they're pointing in the same direction, the cosine similarity is high.
Okay, I think I get that. So if there's a high cosine similarity between two tokens in an LLM, that means those words are pretty closely related in meaning.
Exactly. Like happy and joyful would probably have a high cosine similarity. They'd be pointing in a pretty similar direction in this big multidimensional space. But cosine similarity is only part of the story. Researchers also look at intrinsic dimension.
All right, hit me with it. What in the world is intrinsic dimension?
It's a tough one to explain, but stick with me. Think of a flat piece of paper. It's two-dimensional, right?
Right.
Now imagine crumpling it up into a ball. It might look three-dimensional, but fundamentally, it's still just that same two-dimensional piece of paper. Intrinsic dimension is about figuring out the real dimensionality of some data, even if it's kind of hidden in a bigger space.
So for LLMs, are we talking about like how much space the model needs to represent all the connections between words?
Exactly. Like how do you organize a whole library without losing any books?
Makes sense. So is that all we need to understand this geometry, cosine
Yeah.
similarity, and intrinsic dimension?
Almost. There's one more piece to this puzzle. Neighborhood overlap.
Oh, okay, I'm ready. What's that all about?
Think of it like those friend groups you see in high school. Some kids always hang out together, right?
Yeah.
Neighborhood overlap is about how consistently tokens are grouped together across the different layers of the LLM. Are the same words always appearing together as the model processes information?
So if there's high neighborhood overlap, that means the model has a pretty stable, solid understanding of how words relate to each other, like cat and dog always being buddies.
Exactly. But researchers wanted to see just how important all this geometry stuff really was, so they designed a pretty clever experiment.
Oh, this sounds interesting. What did they do?
They wanted to see what would happen if they messed with the way we naturally use language, almost like creating a word salad.
A word salad. That
Yeah.
sounds chaotic. What did they actually do?
They took normal sentences and mixed up the words randomly. Then they compared the geometry of those scrambled sentences to the original ones.
That's a great idea. I bet that really throws the LLM for a loop.
It did. But before we get into the results, I think it's worth taking a step back. Why should we even care about all this geometry stuff in the first place? What does cosine similarity or intrinsic dimension actually tell us about how well an LLM works?
That's a really good question. It's all very interesting, but is it actually useful?
Well, it turns out all this geometry might actually be connected to something really important: how well the LLM can predict what comes next. In other words, how well it actually understands and uses language.
Wow, that's pretty big. So how do they figure that out? How do you measure something like that?
They looked at something called cross-entropy loss, which basically tells you how surprised the model is by the next word in a sentence.
So if the loss is low, the LLM's a good storyteller, like it knows what's coming next.
Right. And if the loss is high?
It means it's making a lot of wrong guesses.
Yeah. And what they found was fascinating. They found this really strong link between the LLM's internal geometry and how accurate its predictions were. Basically, the more space the model needed to represent relationships between words, the more likely it was to make mistakes when trying to guess the next word.
Huh. So it's almost like it gets lost in its own little world.
Kind of. It has to work harder to make sense of everything. And remember that word salad experiment I mentioned, where they shuffled up all the words in the sentences? That's really where this connection between geometry and prediction accuracy became super clear.
Right, right. So what happened to the LLM's geometry when it had to deal with all those jumbled up words?
Well, first, they saw this big increase in cosine similarity between the
Oh
tokens.
yeah, cosine similarity that measures how aligned the tokens are.
Exactly. And when they mixed up the words, it was like the model had a harder time keeping the meanings of the tokens separate.
So it's like all the words are getting jumbled up in its mind.
Yeah, exactly. It's losing those clear distinctions that are so important in language. But that's not all. They also found that scrambling the words made the intrinsic dimension go way up.
Wait, so messing with the word order actually forced the model to use a bigger space to represent the same information?
Yep. It's kind of counterintuitive, right? You'd think that just moving the words around wouldn't really change how much information there is. But for the LLM, it makes a huge difference.
It's like the model needs a much bigger map to navigate all those scrambled words.
Exactly. And on top of that, they found that shuffling words really messed with the neighborhood overlap.
Oh, right. That's how consistently those groups of words hang out together.
Yeah, and when they scrambled the sentences, the words that normally appear together, like cat and dog, weren't sticking together anymore.
So it's like the LLM was having a harder time understanding how all the words fit together in the sentence.
Right. It was like it lost the thread of the conversation. And all of this had a direct impact on how well it could predict what word came next.
Wow. So cosine similarity, intrinsic dimension, neighborhood overlap, they're all connected to how well the LLM understands language.
It's all about that internal map, that geometry of language. And when that map gets distorted, it just can't function as well.
It's really fascinating stuff. But this is all pretty technical. How can we use this knowledge to actually make LLMs better? I mean, knowing they're sensitive to word order is one thing, but how do we apply that?
Well, that's the million-dollar question. Researchers are exploring new ways to train LLMs that help them build more resilient representations of language, representations that aren't so easily thrown off by changes in word order.
So we need to teach them to see beyond the surface of the sentence and really understand the meaning behind the words, even if they're not in the right order.
Exactly. But it's not just about word order. Remember that connection we talked about between intrinsic dimension and how well the LLM predicts the next word? Well, they actually found that the type of task the LLM is doing can also impact its internal geometry.
Oh, really? That's interesting. So how does the task itself change things?
They look specifically at that last layer of the LLM, the part that's actually responsible for making the prediction. And what they found was that the intrinsic dimension in that final layer was really connected to something called contextual entropy.
Contextual entropy.
Okay.
I don't need you to break that one down for me. What exactly is that?
Well, think about reading a story. Sometimes you can pretty much guess what's going to happen next,
Right.
but other times it's a total mystery. Contextual entropy basically measures that uncertainty.
Got it. So high entropy means lots of possibilities for the next word, and low entropy means it's pretty predictable.
You got it. And what they found was that when the intrinsic dimension was high in that last layer, the contextual entropy was also high. It means the model was less sure about its prediction.
It's all connected. The geometry, the intrinsic dimension, the loss, the entropy, it all plays a role in how well the LLM can make sense of language and generate text. But I have to ask, if LLMs struggle so much with those jumbled sentences, does that mean they're not really understanding language the way we do? Are they just really good at picking up patterns?
That's the big question, isn't it? It's at the heart of this whole debate about whether AI can ever truly understand or if it's just really good imitation. And this research adds a whole new layer to that debate. The fact that LLMs are so sensitive to word order suggests that they are, on some level, picking up on the rules of human language. But whether that means they truly understand, well, that's still a mystery.
So we've learned that the way LLMs organize information is super important for how well they function. And it's not just about making them better at specific tasks. It's about understanding how they work on a much deeper level, maybe even about understanding intelligence itself.
It's pretty incredible stuff. And it makes you wonder what other secrets are hidden inside these models.
I know, right? But before we go too far down that rabbit hole, I want to bring it back to our listeners. Why does all of this matter to someone who's not an AI expert? Why should we care about the geometry of language in LLMs?
Because these things are everywhere. They're in the search engines we use, the news we read, the apps on our phones. Understanding how they work helps us use them better.
And it helps us think critically about the information they give us.
Exactly. Plus, it's just plain cool to think about. These models might seem like magic, but they're built on math and computation. And when you understand those principles, it's like you get a glimpse behind the curtain.
You're right, it is pretty cool. I'll admit I was a little intimidated by all this technical stuff at first, but now I'm really excited to see where this research goes.
Me too. It's a whole new world of possibilities.
Before we wrap up, is there anything else you want to share about working with LLMs? Anything that might surprise our listeners?
Well, one thing that always blows my mind is how the way LLMs represent language actually changes as they process information.
So it's not just static, it's like it's learning as it goes.
Exactly. In the early layers of the model, it's all over the place, like it's trying out different ideas. But then, as it gets deeper, it starts to refine those representations, getting closer and closer to a stable understanding of what it's seeing.
It's like those groups of words are figuring out their relationships as the model learns more about the language.
Yeah, that's a great way to put it. And seeing that evolution, that process of learning and refinement is just amazing. It makes you wonder if these models are doing something more than just crunching numbers. Maybe they really are learning and understanding in ways we don't fully grasp yet.
That's a pretty profound thought. It really makes you wonder what else is going on inside these models.
I know, right? It's what keeps me coming back for more. There's always something new to discover.
Well, I think we've all learned a lot today about how LLMs represent language and how that impacts their ability to do all the amazing things they do. And we've only just scratched the surface. There's so much more to explore.
Absolutely. Who knows what we'll discover next?
Well, before we sign off, I have one final thought for our listeners. Next time you chat with a chatbot or use a tool powered by an LLM, take a moment to think about all the incredible complexity behind that interaction. It's not just a bunch of code spitting out answers. It's a complex system that's constantly learning and evolving. It's a testament to human ingenuity and a glimpse into the future of AI.
I couldn't have said it better myself. And who knows, maybe someday we'll unlock the secrets of language and consciousness hidden within these amazing creations.
Until then, keep exploring, keep asking questions, and keep those brains buzzing. We'll see you next time on The Deep Dive. You know, listening to you talk about how these LLMs learn and adapt, it really makes you wonder, where does all this research ultimately lead us? What's the big picture here? What's the point of understanding the geometry of language in these models?
I think that's a question that a lot of people are really fascinated by. It's like we're not just building tools, we're actually exploring, the very nature of language and intelligence. This research gives us a whole new way to look at these really fundamental ideas.
So it's not just about making our chatbots a little bit better or, our text generators a bit more creative.
It's about understanding the very building blocks of thought itself. Like if we can figure out how these LLMs create meaning, how they learn, how they change, it could completely change the way we think about things, not just in computer science, but in other fields too. Like imagine what it could do for education or psychology.
Yeah, that's a good point.
Yeah.
But let's zoom out for a second and think about our listeners. What does all this mean for someone who's not a researcher, who isn't, deep in the world of AI and linguistics? Why should they care about this geometry of language stuff?
Because it's all around us. I mean, think about it. LLMs are everywhere. The search engines we use, the news articles we read, understanding how these things work, what they're good at, where they struggle, it helps us use them better and think critically about the information they give us.
So it's about becoming more informed users,
Right.
not just taking everything at face value.
Exactly. Plus, it's just pretty amazing to think about. These models might seem like pure magic, but under the hood, it's all math and computation. And understanding those principles, I think, gives you a deeper appreciation for what's possible, but also for the challenges.
I totally agree. I'll admit, when we started this deep dive, I was a little overwhelmed by all the technical jargon,
Hmm.
but now I'm actually pretty excited about the future of LLMs and what they might be able to teach us about ourselves.
I think that's the amazing thing about exploring new ideas. Sometimes you have to push past that initial discomfort, to get to the really interesting stuff.
Well, I think it's safe to say we've all come away with a better understanding of how LLMs work, how they represent language, how that impacts their performance. It's
It
complicated.
is. But, I think we just scratched the surface today.
Exactly. So to wrap things up, I have one final thought for everyone listening. Next time you're interacting with an LLM, whether it's a chatbot or something else, think about the incredible complexity going on behind the scenes, all those calculations, all that data, all coming together to create something that seems so simple and effortless. It really is a testament to human ingenuity and a glimpse into what might be possible with AI.
Absolutely. And then who knows, maybe someday we'll unlock the secrets of how language and consciousness really work, all thanks to these incredible creations.
Well, on that note, we'll leave you to ponder that. Keep exploring, keep asking those questions, and keep your brains buzzing. We'll see you next time on The Deep Dive.